Hello everyone, I'm Zhihao, and both Fanxing and I are the first authors. In this talk, I will present a novel tree modeling approach based on 3D sketches. Trees are hard to model due to their complex geometry. Many progress has been made over the years in tree modeling, but there remain many challenges. Procedural tree modeling requires botanical expertise and is difficult to control the shape. By contrast, sketch-based tree modeling is more intuitive, but previous methods are all based on 2D sketches using devices like mouse and tablets, and they cannot guarantee to generate possible depth values and 3D tree shapes. And here we want to develop a novel sketch-based tree modeling system. It should be intuitive and easy to use, with flexible control of the overall shape. Also, the instantaneous feedback, that is the 3D display of the tree model following sketching, is essential for providing a fluent user experience, especially for artists during the conceptual design stage. Like this, it is hard to design a tree targeted to letters V and R at the same time. Since the trees are complex in geometry with many branches, it is extremely labor-intensive and difficult to draw all the details. Our main idea is that the user controls the overall tree shape by 3D sketching, while the detailed branches are automatically synthesized using a rule-based method. The user just needs to draw the main characteristics of a tree, including main trunks and the envelopes of foliage. This little video shows the process of creating a tree using our method. Now let me introduce our method. First, we generate lobes from 3D strokes. Here is an example of the process of lobe generation. We perform the point-to-point matching for any two neighboring strokes. The match is updated immediately following sketching. Before matching points, we need to determine a starting point pair on the two strokes. An intuitive idea is to choose 2 points that have the nearest Euclidean distance, but for this case, this method finds a bad pair that will produce wrong match strips. However, the ideal pair should be like the right one. We found that the barycentric direction is a good feature to find the starting pair. The barycentric direction of a point is a vector towards the barycenter of the stroke, and the black lines here represent the barycentric directions of all the points. The starting point pair are the points with a closed barycentric direction. We mark this pair with blue rectangles. Then, starting with this pair, we could perform point-to-point matching to generate match strips. And this video shows the robustness of our algorithm. The user can greatly move the strokes. We also provide two editing tools. Including stroke editing and match deformation to adjust the shape of lobe. Here are 3 resulting lobes generated by our method. Then with the requirements of the real-time interaction, we use a simple method to generate the 3D tree model in seconds. Given the user draw main trunks, we sample the nodes uniformly from each stroke. A node is a point composing a branch and probably producing new branches. Then we will generate branches recursively to fully fill the lobe. At the beginning of each iteration, we first cluster the points on the lobes by associating each point with the nearest branch node. The resulting clusters are marked with different colors, and the points that have no associated point are considered dyed in current iteration. Also, the clusters can be then divided into small ones. Next, according to the clusters, we can produce new branches from each node. The growth direction is computed as the weighted average of the vectors formed by the branch node and the cluster points. And finally, we choose an appropriate substrate from a predefined database and attach them to each node. The algorithm will repeat until the lobe is fully filled with branches. And the results. We show several modeling results according to several Baoquan trees. And the user can also freely place lobes to explore more designs. Here are 2 swan-shaped trees flapping their wings to different angles. And the user can even design a tree targeted to letters V and R at the same time. And here are more tree models with artistic shapes. And additionally, we also provide an option for users to get trees directly from external 3D models. And for the comparison, we firstly compare our method with a 2D sketch-based method. Their method asks the user to carefully draw a large number of strokes to represent the tree skeletons. For this example, the user has to draw more than 80 strokes and take more than 1 minute for inference steps. But our method can produce a similar tree from only a simple lobe and a few trunks, and the tree growth is almost in real time. And we also compare with a method called tree sketch with create trees on a tablet. Limited by 2D interface, their tree models often look flat from a side view, but our method can be designed more freely with the benefit of mid-air sketching. And for user evaluation, we invited 10 participants to experience the following 3 systems and fill out the questionnaires. The questionnaires focus on 3 questions regarding the ease of use, satisfaction, and creativity. And this, yeah, okay, I will finish it quickly. This chart shows the statistical result, which indicates our system was better rated than others. Additionally, to observe how modelers communicate shapes, the participants were also asked to create a 3D tree model according to the left photo. Here are some modeling results. And in summary, this is the first exploration of a VR-based interface for realistic tree modeling. Our method combines the user's high-level inputs and automatic generation of branches. And this enables even novice users to model a tree just by focusing the overall tree shapes. And it's the end of my talk. Thank you all very much.